Hi people, welcome back to the channel. Today I want to show you how to benchmark your FPGA, i.e. how fast the FPGA will go. Now you can open the datasheet and it's kind of hard to find how fast it goes because most of the speed numbers there are for blocks in isolations. So let's say the DSP block goes 500 megs, yeah it does. The flip-flop they go 500 megs, yeah maybe. But when you put everything together and a little bit of routing is getting involved, those numbers, they start to look different. So I put a very simple benchmarking here, and it's a bit skewed. It's not going to tell you the whole story, but it's going to tell you some. So it's a counter. We start with 8-bit counter, and we try to achieve 500 megs. We're not going to get that. And then we increase the counter, and things they get a little bit slower, and we figure out why it's slower, and we start cutting a little bit our expectations, and we get to a point where we think it's okay. Now this design is not, let's say, a proper design because it's very nicely placed by the tools. So it's a vertical placement of the flip-flops and the carry chain. They're nicely arranged, but it will tell you something. It will tell you that if you're coding something and you get like 30 megahertz out of that, there is something wrong with your coding, because 200 meg is achievable. Everybody knows that. Even 300 meg, if you are careful, if you understand exactly how the FPGA works and all the inside the job or under the hood, you will learn how to code carefully. So the device that I'm using today, it's a ZYNQ ZYNQ device, which is basically an Artix. It's a small ZYNQ. So let's say this is an Artix device. This is not a fast device by any means. It's a fairly old device, so you might get architecture which are way faster those days. If I'm not mistaken, I think it's somewhere like 20 or 28 nanometers. I don't know, but in that range. So today you can buy things which are 10 nanometers, way faster. Anyway, that's not the point. The point is you need to learn, you need to figure out how fast is your FPGA that you are targeting. You need to set some expectations, and if you get nasty, way below results, that you need to adjust your coding, or you need to learn a little bit more. So let's go on. Now, how do we benchmark the FPGA? I wrote a very simple counter, an 8-bit counter. This counter is going to be implemented using carry chain logic. So we have two types of counter, ripple counters and carry chain. On FPGAs you will always get a carry chain counter, and I'm not going to explain why in this video, maybe in another video. So 8-bit counter, nothing complex here. I connected an output from the MSB of this counter to make sure things they don't get optimized out. What do I mean by optimized out? If you have dangling signals which they're not going to go to output, the tools they are going to consider then that you are not going to use them, and they're going to be exterminated. Now we have a constraints file. This constraints file specifies the pin location for the clock where it's entering the system, and some other, the IO standards of the pins of the IOs. But so we don't care about this part that much. It is just to make sure that the tools are not going to scream. What we are focusing on is this line. Now this line specifies our clock. So I'm going to specify here. Let's start very optimistic, let's say. So I'll put here what? Let's go 2 nanoseconds. 2 nanoseconds. Our period of the clock is 2 nanoseconds. Sorry, there's a comma here. 2 nanoseconds, and of course the waveform, it's 1 nanosecond, the semi-period. So this, why do we need both of these? So this will define the frequency, and this will define the duty of the clock. So 50-50, 1 nanosecond up, 1 nanosecond down. Anyway, so let's go and implement this. So I save all those, only two source files. So we are aiming on a 500 meg clock. We are hoping this counter will work with 500 meg. Let's see what is going on. So I'm just going to go run implementation. Okay, let's see what we got. So let's open the implemented design. I say okay here. One critical warning message: the design failed to meet timing requirement. We were kind of expecting this. It's not going to run at 500 megs. Now let's see what it failed actually. Say okay here, and we have here on the timing on messages, we have the timing summary, right? So you click here on the timing tab and you get this summary and you get those bullets here. All right, so check timing. Let's see where is actually the problem. Where is the problem? Intra clock path, right? So it's saying here that we failed by a decent margin, actually not that much. It's 155 picoseconds or 0.155 nanosecond. That this is our slack or a negative slack, let's say. So now let's see exactly what actually has failed. So if we drill down here, so and we click on this, okay, so it's saying that there is a buff G. Buff G stands for a buffer, a global buffer for the clock, but there is an I here, which means that this is actually the IO. So what basically this line is trying to tell is that, oh, you will never pass such a fast clock through this component. Now, how do they know this? Because they have a model, a timing model of the device. So every time when you say, okay, I want to use this FPGA and this speed grid and whatever, it loads from the disk the description and timing for all those tiny little components you have. And it's checking against your design. Oh, he wants a 500 meg clock. Oh, but my buff G component here doesn't accept that much, so it's failing by whatever. So if we look here, okay, so we need to go down at least 150 picoseconds with our requirements to make this work. Well, let's do that. We go here on the XDC file and let's add 200 picoseconds, right? So and here, of course, we need to hand 100 because this is a semi period. So this is always half of that. We go save and we go run implementation. Again, it's saying that the old device, close the old device, and we wait. And we wait. And we got some results. We open the implemented again. And oh, all user specified timing constraints are met. So we lower down the clock, but now we are on the pass. We are passing. Wow, 445 megahertz. That's a lot, right? That's very, very fast. Well, I'm not so sure. Let's see what we got here. So let's see on the device what we actually got. So how do we see on the device? If we click here on the device, this is the bird's eye view of the Artix or the Kintex or whatever FPGA you're using. This is the neighborhood. Let's call it the Artix neighborhood, right? And those are small blocks in your neighborhood. And those are some streets here. I'm going to now let's see if you can see everything which is in your design by just going here, and those are all the elements in your design, right? Now it's kind of boring list here to see all this. You can see on the schematic level, if you click here on the schematic, to show the schematic of your. So let's see what we can recognize here. Oh, 4 flip-flops, a carry chain, another carry chain, another 4 flip-flops. Kind of makes sense. 8-bit counter. Now this is the clock getting in the system. This is the component which was actually creating troubles, right? This is the buff G, the buffer global clock distributor. Let's click on it to see where it's on the device. So if I click on it and I go now to the device, it should be highlighted. Apparently it's not. Is it good? If I double click on it, maybe. Let's go zoom to Oh yes. So now if you click zoom to selection, so this is our component. This is the guy who was failing. Was our trouble. Let's zoom out to see where it is. Wow, it's somewhere in the middle of the device. Such a, I don't know, simple component. Anyway, he can't take more than 400 and what we put there, 450, around 450. Now why? You may wonder. Because this clock goes to many flip-flops, and if you don't believe me, I'm going to click on the clock and I'm going to zoom out and let's see where it goes. Where it goes here and it ends up here. This is where most of our design is. So if we zoom, oh, those are our flip-flops. So the clock goes to all those flip-flops, you see. So this clock is driving many flip-flops. Imagine that you have 500,000 flip-flops, right? So it goes everywhere. So it's going to fan out to so many loads. Anyway, okay, let's go back to the schematic. Where we have the schematic, and let's click on a flip-flop. I want this fella. And we go back to the device view, and I go here again. Show me what is selected. Oh, that's our guy. That's our flip-flop. Right? So you can trace the different components in your netlist. Now, it's not going to help you much, but let's look at other things. Let's look at routing. So let's see how this flip-flop is actually, what is getting. Well, it's getting the data line, it's getting the control enable, it's getting, so there are a bunch of things. This is the output. So you can highlight. Now, you see those lines actually that are coming through those muxes. So, okay, well, what is this mux? So this mux can actually choose this signal to come from there. So it's like, they're like small junctions. Now, let's see where he's getting this signal from, this mux. So it's coming from here, this is the carry chain logic. I'm not going to go in detail again. So it's coming from somewhere else. But look, everything that you see in green here, they're actually signals in your design. And you see this zigzagging here. You see that actually it's a box here. It's a component here. I'm not sure if I can highlight. Yes, I can highlight it. This is like imagine this is a breadboard and we put wires. So this is the configurable part. Those horizontal lines, they're actually not configurable. They're actually metal lines in the IC. This is the configurable part. This is what the bitstream is actually controlling, which comes from where and how they get routed. You have to keep in mind that there is a delay. This box actually incurs a delay because there are transistors which they switch those routes. So the same thing here with those muxes, right? Those are actually transistors here which they choose the path. So it's going to be a tiny little delay penalty here for this signal. The same here, not to mention in the actual components, but on the routing there are going to be delays. Now, if you see here, this is a bigger box. More delays here. So every single route will have some delays. So you will have two types of delays. The component delays, what we've seen with the buff G, that okay, I can work with 450, I can't go faster. And then you will have those delays, which they're not big delays, but they add up because look, a signal might cross this box and then it's going here and it's crossing this box. So it's going to be a delay here on this box. It's going to be another delay here on this box. And then it's going to be the actual component delay. So all those things they add to panel. So if you have a signal which is coming from Cuckoo Land and it has to cross the whole neighborhood and it's going through a few of those boxes. Now you may see here that there are actually very long lines here. So it doesn't go box. It's just going, there are long lines, shorter, and so on. So the tools are actually very clever to go on they're called global routing and go on the local routing, which actually those tiny little junction boxes, right? So there will be delay, two types of delay, routing and logic. Okay, now let's make it fail. Timing, how we are going to do that? We go to the VHDL. And we make this counter bigger. So we say, okay, do you know what? I'm done with 8-bit counter. Let's go mad, 20-bit counter. So 19 to 0, that means 20. Oh no, let's go even further. Let's go 28. I'm going in increments of 4 because there are 4, the carry chains, there are 4 bits. So let's go like that. So 20, no, let's 23, 24 bits. Sorry, 23 here. and I'm going to connect here to the MSB, which is 23. So I go again, save. We are still aiming for what? For 445 megahertz. And we go and hit run implementation. And we are back again, and we say on implemented design. And guess what? We failed timing again. Why? Well, let's see why. Let's see where we failed timing. So we go here and intra-clock paths, clock, setup. Okay, so it looks like on this path we are actually failing by what? By a very small amount, by 65 picoseconds. That's not much. 65 picoseconds, right? And where is this going? Oh, it's going to a flip-flop, I think. Counter reg 21 and 23. Those are quite high, so they are the MSBs. What this is actually telling me that, okay, you know what? Things they propagate, they have to propagate to the carry chain, to those MSBs, so probably we need to slow down a bit. So let's take the worst case scenario, 86 picoseconds. Let's make it 100 picoseconds to play. I say 3 nanoseconds, and let's go here, 1.5, I think, yeah, 1.5. Okay. That's 3 nanoseconds, that's 333 megahertz. Yeah, save. Implement. Silly me. Let's see now. Ah, we pass. And we have passed with good margin. So we might even go faster. But let's not go faster. Let's see how the design looks like. VHDL, and let's make it 32-bit. 31 here, and connect the 31 to the LSB to the output. Save, implement, bang, yes. And back again, and bang. So this is a 32-bit counter. It's not failing timing. So it's a decent size counter. They're not, I don't know many cases where you need such a large counter, but it's with localized routing, so it doesn't go across the chip, so it's not exactly real case scenario. But yeah, that's 333 megahertz. That's a decent speed, I would say, for a counter, for a 32-bit counter. Now let's push a little bit this. Let's calculate what should we put for 350. So we go 350 megs. 1 over this, where is that 1 over? So it's what, 2.85 nanoseconds. So let's put here 2.85, 2.85 nanoseconds, and what's this, the half of that? 2.85 divided by 2, 1.25. So 1 point, sorry, where was it? 1.425, 425, save. So we are aiming 350 megs with a 32-bit counter, go. And we got results. Let's see how they look like. Okay. Yeah, it passed. So 350 megs are achievable. 32-bit counter, localized routing. So we know those flip-flops and carry chains, they can work. 32-bit carry chain, it's 32-bit long carry chain, can achieve 350. That's not bad. So as a conclusion, I think 300 megahertz are achievable. And if you are getting much lower results, let's say below 100, probably there is something wrong with your design, and you should check if you don't have too many levels of logic, or the routing, the design is getting congested. Your timing report will tell you where the time is spent, so have a look at that and try to figure out where the problem, so you know what to fix. I hope you enjoyed the video, I hope you learned something, and I shall see you on the next one.